Venus takes 243 Earth days to turn around once. Earth does it in 24 hours. Mars about the same. Jupiter, the biggest planet we've got, spins so fast it does a full turn in under 10 hours. And Venus, 243 days, longer than its own year. A day on Venus is longer than a year on Venus. Already that should bother you. But that's not the strange part. The strange part is the direction. Venus spins backwards. Every other planet, with one weird exception I'll get to, spins the same way, counterclockwise. If you're looking down from the north, the sun spins that way, the planets orbit that way, and they rotate that way, all of them turning together like children on a merry-go-round. Except Venus. Venus goes the other way. If you could stand on the surface, which you can't because you'd be crushed and cooked and dissolved in acid, but if you could, you'd see the sun rise in the west. Think about that. The sun comes up in the west on Venus. Something went terribly wrong with that planet, and nobody can tell you exactly what it was. That's what I want to talk about today. Because this isn't just an astronomical curiosity, some little footnote in a textbook about planetary trivia. This is a clue about what happened during the formation of the solar system, about forces and collisions in physics, on a scale that's almost impossible to imagine. And the honest truth is we haven't solved it. We have suspects. We have theories, but we don't have a conviction. So let me take you through the evidence, piece by piece, and you tell me what you think happened. First, let's establish what we should expect, because to know that something is wrong, you need to know what right looks like. Imagine a vast cloud of gas and dust out there in interstellar space, light years across, cold, dark, drifting. And suppose gravity begins to win. Little by little, the cloud starts to collapse inward. It's a slow process at first, but the cloud has a secret. It's not perfectly still. Somewhere, some part of it has a slight rotation. Maybe it got nudged by a passing star. Maybe it was stirred by the shock wave of a distant supernova. Doesn't matter. What matters is that there is some angular momentum in the cloud, even a tiny amount. And here's where one of the deepest principles in all of physics takes over. Conservation of angular momentum. It says that the total amount of rotational motion in a system stays the same provided nothing from the outside is applying a torque. The spinning cloud collapses, it gets smaller, and because angular momentum is conserved, it must spin faster. You've seen this happen. An ice skater doing a pirouette pulls her arms in and she spins faster. She didn't push anything. She didn't add energy from somewhere. She just made herself smaller, and the conservation law did the rest. Her moment of inertia went down, so her angular velocity went up, and the product of the two stayed constant. The same thing happens with the cloud. As it contracts under gravity, it spins faster and faster, and the spinning flattens it out into a disk. The material at the equator of the cloud has more angular momentum and resists falling inward, so it stays out and forms a wide, flat, rotating disk, a protoplanetary disk. And everything in this disk, every grain of dust, every pebble, every clump that will eventually become a planet, is moving in the same direction, counterclockwise from the north. The sun forms at the center, spinning counterclockwise. The planets coalesce out of the disk, orbiting counterclockwise. And as these planets grow, accreting material from the disk, they pick up the angular momentum of that material, and they spin counterclockwise too. Everything in the solar system carries the signature of that original rotation. It's like a family resemblance. You know, you look at Earth spinning, you look at Jupiter spinning, you look at Mars spinning, and they're all saying the same thing. We came from the same place, and that place was turning this way. And by the way, this isn't just theoretical. We can see this process happening right now in other solar systems. We have telescopes that can image protoplanetary disks around young stars, and they're exactly what the theory predicts. Flat, rotating structures with gaps where planets are forming, all going the same way. The physics works. It's been tested. Conservation of angular momentum is not a suggestion. It's a law. So when you look at Venus and you see it going the other way, the first thing you should feel is deep suspicion. because angular momentum doesn't just reverse itself. It's not like a ball that bounces off a wall and comes back the other direction. That reversing a planet's spin is like taking a spinning flywheel weighing a billion kilograms and somehow making it stop and turn the other way. To do that, you need to apply a torque, and you need to apply it for a long time, or you need to apply it very, very hard all at once. Those are your two options. Either something hit Venus like a hammer and reversed the spin in minutes, or something has been gently, persistently twisting Venus the other way over billions of years. A violent crime or a slow conspiracy. The question is which, and the question is whether we can ever find enough evidence to be sure. Now, before we get to the theories, let me tell you something about Venus that makes this whole mystery even more peculiar and more frustrating. We didn't even know Venus spun backwards until 1962. Think about that. Venus is the closest planet to Earth. It's been one of the brightest objects in the sky since human beings first looked up. The ancient Babylonians tracked it across the sky. The Greeks noticed it appeared both in the morning and in the evening and thought it was two different stars. The morning star and the evening star, they named them both, and it took them a while to realize it was the same object. We've been staring at Venus for thousands of years, and we couldn't tell which way it was spinning until the Kennedy administration. Why? Because Venus is wearing a disguise. It has the thickest, most opaque atmosphere of any rocky planet in the solar system. The surface pressure is about 93 times the pressure of Earth's atmosphere. 93 times, that's like standing a kilometer deep in the ocean. If you went to Venus, the air would crush you long before the heat got you, and the heat would get you fast, because the surface temperature is around 465 degrees Celsius, hot enough to melt lead, hot enough to melt zinc, hotter than Mercury, even though Mercury is much closer to the sun. That's the greenhouse effect, run completely amok. 96% of Venus's atmosphere is carbon dioxide. The remaining few percent is mostly nitrogen, with clouds of sulfuric acid floating in the upper layers. Not water clouds, sulfuric acid. You can't see through that. You cannot look at Venus with an optical telescope and see its surface. When astronomers in the 17th and 18th centuries pointed their best instruments at Venus, all they saw was a blank white disk. Brilliant, featureless, maddening. Giovanni Cassini, one of the finest observers who ever lived, tried to measure Venus's rotation in 1666 and 1667. He thought the period was less than a day. He was wrong by a factor of about 240. Other astronomers over the next 3 centuries made their own guesses. Some said 24 hours, figuring Venus was probably like Earth. Some said about 25 days. Everyone was wrong. The planet kept its secret. It wasn't until we had radar that we could pierce through those acid clouds. In the early 1960s, teams at the Jet Propulsion Laboratory and elsewhere bounced radar signals off Venus and measured the Doppler shift of the reflected signal. Radar doesn't care about clouds. The radio waves go right through and bounce off the solid surface. By measuring how the frequency of the return signal was spread out, you could figure out how fast the surface was moving and in which direction. Now think about how clever this is. When you bounce a radar beam off a spinning planet, the side of the planet that's moving toward you reflects the signal at a slightly higher frequency. Doppler shift. The side moving away reflects at a slightly lower frequency. The width of that frequency spread tells you the spin rate, and the asymmetry tells you the direction. If the planet is spinning in one direction, the higher frequency side is on the right. If it's spinning the other way, the higher frequency side is on the left. The radar doesn't lie. It doesn't care about clouds or theories or expectations. It just measures the motion. And what they found shocked the astronomical community. The rotation was not just slow, it was retrograde, backwards. 243 Earth days. The planet rotates more slowly than it orbits the sun, and it rotates in the wrong direction. Nobody expected that. Richard Goldstein published the result in 1964. Some people thought the measurements were flawed. They weren't. Now, let me be precise about what backward means, because there's a subtlety here that matters. Astronomers define the north pole of a planet by the right-hand rule and its orientation relative to the orbital plane. By that definition, Venus's axis is tilted 177 degrees from vertical, almost completely upside down, only 3 degrees away from being perfectly inverted. So you could describe the situation in two ways. You could say Venus rotates backwards, or you could say Venus is flipped nearly upside down and rotates normally, but since it's upside down, the rotation appears reversed when you look at it from the outside. Either description is correct, they're mathematically equivalent. But the distinction matters when you're trying to figure out what happened. Did something reverse the spin? Or did something flip the whole planet over? These are different physical processes, and they would leave different traces. So we have our mystery. 4.5 billion years of solar system history, and Venus ended up spinning the wrong way. Let's examine the suspects. Suspect number 1, the giant impact. The idea is simple and dramatic. Early in the solar system's history, things were not neat and orderly like they are now. Things were chaotic, violent, catastrophic. The planets were still forming, sweeping up debris, and there were leftover protoplanets, objects the size of Mars or bigger, careening through the inner solar system on unstable orbits. Collisions were common. We think this is how Earth got its moon. A Mars-sized body, which we call Theia, slammed into the early Earth at an angle roughly 4.5 billion years ago. The impact was so violent it vaporized rock, sprayed molten debris into orbit, and that debris coalesced into the moon over the course of centuries. We have strong evidence for this. The isotopic ratios in moon rocks brought back by the Apollo astronauts match Earth's mantle almost exactly. The chemistry tells the story the way a fingerprint identifies a suspect. If something like that could happen to Earth, why not Venus? The idea is that a massive body hit Venus, either head-on or at just the right angle, and either flipped the planet upside down or slowed its spin so dramatically that it ended up going backwards. Picture a top spinning on a table. If I flick it from the side hard enough, I can either knock it over entirely so it's now spinning upside down, which looks like backward rotation, or I can slow it to a stop, and then it topples over and starts turning the other way. Either mechanism works. And notice this connects to that subtlety about the tilt. If Venus was hit and flipped to 177 degrees, it wasn't really reversed, it was toppled. Like a gyroscope that gets knocked past 90 degrees and falls all the way to the other side. The spin direction relative to the planet's own body didn't change, but relative to the rest of the solar system it looks backward. And there's something very appealing about this theory. It's violent, it's dramatic, it solves the problem in one blow, literally. And we know from the cratering record that giant impacts happen throughout the early solar system. Statistically, it would be surprising if Venus never experienced one. But there are problems. Serious, nagging problems. First, where's the evidence? When Theia hit Earth, we got the moon. An enormous, magnificent, undeniable piece of evidence hanging in the sky every single night. Venus has no moon. None. Zero. Not a captured asteroid, not a chunk of debris, nothing. If a giant impact reversed Venus's spin, what happened to all the debris? Some researchers say the impact was nearly head-on, so it wouldn't fling much material into orbit. The energy goes into heating and deforming the planet rather than ejecting debris. Others say debris did get ejected, but it fell inside the synchronous orbit. See, here's the thing. Because Venus rotates so slowly, the synchronous orbit, the distance at which a moon would orbit at the same rate the planet spins, is extremely far out. Any debris disk that forms close to the planet is inside that boundary, and material inside the synchronous orbit doesn't get pushed outward by tidal forces the way our moon is being pushed away from Earth. Instead, it spirals inward and falls back onto Venus. So any moon that formed would have been temporary. It would have been consumed by the planet. There's even a provocative hypothesis that Venus once had a moon formed by a first impact, and then a second impact destroyed that moon, or that the tidal interaction with the sun destabilized it. But now you're stacking hypotheses on top of hypotheses like a tower of playing cards, and in physics that should make you nervous. Every additional assumption you add is another way for the theory to be wrong. And there's a deeper philosophical issue. Recent computer simulations from 2025 show that yes, a wide variety of giant impacts can produce Venus's current rotation period. Head-on collisions, oblique collisions, big impactors, small impactors, fast impactors, slow impactors. All sorts of scenarios work. The problem is that too many scenarios work. When your theory can accommodate almost any observation, it's not really constraining anything. It's like a suspect who has an alibi for every crime because he says he was everywhere at once. The theory is consistent with Venus's rotation, but consistency is not the same as evidence. In physics, I always want to distinguish between an explanation and a description. An explanation tells you why something happened. A description tells you that it could have happened. The giant impact theory gives us a description. It doesn't give us a fingerprint. So let's turn to suspect number 2. This one is quieter, slower, subtler, and in many ways more elegant. It involves tides, not ocean tides. Venus doesn't have oceans. Atmospheric tides. Here's the setup. Venus is close to the Sun. Not as close as Mercury, but close enough that the Sun's gravitational pull is strong. This gravitational pull deforms the solid body of Venus slightly, creating a bulge, a tidal bulge. Think of it like squeezing a tennis ball between your thumb and forefinger. It gets elongated along the axis of the squeezing force. The Sun does the same thing to Venus, creates a slight elongation pointing toward and away from the Sun. Now, if Venus is rotating, even slowly, this bulge gets dragged a little bit ahead of the line connecting Venus to the Sun. The planet rotates and the bulge tries to follow, but there's friction inside the planet, so the bulge can't keep up perfectly. It gets displaced, and the Sun's gravity acting on that displaced bulge creates a torque, a braking torque. It slows the rotation down. This is gravitational tidal dissipation, and over billions of years it's relentless. It would tend to slow Venus down toward a state where the planet is tidally locked to the Sun, with one face always pointing sunward. Like Mercury, almost. Mercury is in a 3-to-2 resonance with the Sun because of this process, rotating 3 times for every 2 orbits. But Venus is not locked to the Sun, it's spinning backward. So something is fighting the gravitational tides. Enter the atmosphere. Venus has this colossal, dense, superheated atmosphere, and the Sun heats it. Not uniformly, the sunlit side gets hotter. This heating creates a pressure bulge, a region of higher pressure on the day side. But the atmosphere has thermal inertia. It takes time to heat up and time to cool down. So this pressure bulge doesn't sit right at the subsolar point, the spot where the Sun is directly overhead. It gets shifted. It's displaced from the Sun's position by the rotation of the planet and the sluggish thermal response of all that carbon dioxide. And here's where it gets interesting. This shifted atmospheric bulge creates its own torque on the planet. And it turns out that this atmospheric torque pushes in the opposite direction from the gravitational torque on the solid body. The gravitational tides on the rock pull in one direction, trying to slow Venus toward tidal locking. The thermal atmospheric tides push the other way, nudging Venus in the retrograde direction. Why retrograde specifically? Because of the geometry of the heating. The thermal bulge displaced by Venus's rotation and the slow thermal response of all that dense carbon dioxide ends up positioned in such a way that the Sun's gravitational pull on it creates a torque opposing the locking. The details involve phase lags and the specific thermodynamic properties of supercritical carbon dioxide, but the bottom line is elegant. Venus's own atmosphere acts as a shield against being tidally locked to the Sun. You've got a tug of war. 2 forces, 2 bulges, 2 torques pulling against each other. Let me give you an analogy that might help. Imagine you're in a swimming pool, floating on a lazy river ride. The current is pushing you one way, but there's a wind blowing across the surface pushing you the other way. If the current is stronger, you drift with the current. If the wind is stronger, you drift with the wind. But there's a sweet spot where the wind and the current exactly balance, and you just sit there barely moving or drifting very slowly in one direction. That's what's happening to Venus. The gravitational tide is the current. The atmospheric tide is the wind. And Venus has found the sweet spot where they almost cancel. The residual, the leftover, is a slow drift in the retrograde direction. And the beautiful thing is that they can reach a stable equilibrium. Not the equilibrium of tidal locking, where Venus stops rotating relative to the Sun, a different kind of equilibrium, one where the planet slowly rotates in the retrograde direction, backwards. This idea was first proposed in 1969 by Thomas Gold and Stephen Sauter, and it was developed with mathematical rigor by Alexandre Correa and Jacques Lascar, starting in 2001. What Correa and Lascar showed is that when you account for the gravitational body tides, the thermal atmospheric tides, and the dissipation at the boundary between Venus's mantle and core, the planet's rotation can evolve from almost any starting condition into one of exactly 4 possible end states. Think of it like a marble rolling on a hilly landscape. No matter where you start the marble, it ends up in one of 4 valleys. 2 valleys are prograde, 2 are retrograde, and the retrograde valleys are deeper, more stable. The 2 retrograde states both have rotation periods of about 243 days. The 2 prograde states have periods of about 77 days. Venus appears to have rolled into one of the retrograde valleys and settled there. No collision needed. Just the patient, relentless billion-year work of the sun's gravity pulling on Venus's body and heating Venus's atmosphere, fighting each other to a standstill, and the standstill happens to be a slow backwards rotation, like a top that's been spinning in thick syrup, gradually slowing, wobbling, stalling, and then ever so gently beginning to turn the other way. Let me make sure you understand how weird this is. It means that the backward rotation of Venus might not be an accident at all. It might be an attractor, a natural resting place. If you could go back in time and give Venus a different starting spin, faster, slower, tilted differently, the planet would still evolve toward one of these 4 states. The current rotation is not a random outcome of some chaotic event. It's a destination. The forces acting on Venus are funneling it toward this particular spin state, the way water flows downhill regardless of where you pour it. Different paths, same endpoint. And here's what's genuinely surprising. The theory predicts that the current state, this slow retrograde rotation, is not unique to Venus's specific history. Any rocky planet of similar mass, at a similar distance from its star, with a sufficiently thick atmosphere, would tend to end up in a similar configuration. That's a testable prediction, in principle. As we discover more rocky exoplanets close to their stars, we might find that retrograde rotation is common. It might not be an anomaly at all. It might be a feature. I find that beautiful. A catastrophe leaves scars, but this process is invisible, silent, taking place over geological time, with nothing to see, just the slow victory of one torque over another. But is it right? Well, it has one very appealing feature. It explains the current state of Venus using forces that we know are acting right now, right this minute. We're not invoking a hypothetical event 4 billion years ago that left no visible trace. We're pointing at the sun and saying, you did this, you're doing it still, and we can calculate it. But the theory has its own problems. The big one is the initial conditions. If Venus started out spinning fast like most of the other planets, once every few hours, the atmospheric tides might not have been strong enough to overpower the gravitational tides within 4.5 billion years. Depending on which model of tidal dissipation you use, Venus needed to start with a rotation period somewhere between about half a day and 3 days for the atmospheric tides to do their work in time. Shorter than that, and the planet would still be spinning prograde today, just slowly. The atmospheric tides would be fighting but losing. So what slowed Venus down initially? Maybe a moderate impact. Not the planet killer we talked about before. Something smaller, enough to knock the rotation from a few hours to a couple of days, and then let the atmospheric tides take over and finish the job. That's a hybrid scenario. The impact didn't reverse the spin. The atmosphere did. But the impact set the stage. And this is maybe the most honest answer we have. Not one suspect acting alone, but 2 suspects working together. A conspiracy. The impact softened Venus up, and the atmosphere delivered the final blow. It's less dramatic than a single cataclysmic event, and it's less elegant than pure tidal evolution. But nature doesn't care about our preferences for clean narratives. Nature does what the forces dictate, and the forces on Venus are complicated. multiple processes acting over different time scales, each contributing a piece of the story. That's usually how physics works in the real world. Not one cause, but many, layered on top of each other, interacting in ways that resist simple description. There's another clue I haven't told you about yet. Something genuinely eerie. Venus is still changing its rotation. Right now, we measured it in the early 1990s. NASA's Magellan spacecraft orbited Venus and mapped the surface with radar over 4 years. From the way surface features rotated beneath the spacecraft, scientists calculated the rotation period as 243.0185 Earth days. Very precise. Then 16 years later, the European Space Agency's Venus Express arrived. Scientists used its infrared instruments to peer through the atmosphere at the surface and compare what they saw to the Magellan maps. The features had shifted up to 20 kilometers from where they should have been. The planet had slowed down by about 6.5 minutes. Over 16 years. That's a tiny change in absolute terms, but for a planet, it's astonishing. Earth's rotation changes by milliseconds per century, and most of that is from the moon slowly stealing our angular momentum. Venus changed by minutes per decade. Something is actively wrestling with Venus's spin. The prime suspect for these short-term fluctuations is the atmosphere. Those ferocious winds. In the upper atmosphere of Venus, winds blow at 360 kilometers per hour, circling the entire planet in just 4 Earth days. 4 days. The surface below is barely moving, creeping through one rotation in 243 days. Stop and think about how strange that is. The atmosphere is spinning 60 times faster than the planet it sits on. That's called superrotation, and it's one of the most bizarre phenomena in the solar system. On Earth, our atmospheric winds are driven by differential heating. The sun warms the equator more than the poles, and this sets up circulation patterns. But Earth's atmosphere never spins faster than the planet underneath it. The surface drags the atmosphere along. The atmosphere couldn't outrun the ground even if it tried. On Venus, somehow the atmosphere is broken free. It's whipping around the planet at ludicrous speed while the surface barely turns, and we don't fully understand how. There's no obvious energy source big enough to drive winds that fast. The sun's heating should create some circulation, but the models can't quite reproduce the observed wind speeds. Something in the dynamics of Venus's thick, hot atmosphere creates a positive feedback loop that accelerates the winds far beyond what you'd naively expect. And these winds matter for the rotation problem because that enormous mismatch between the atmosphere and the ground means there's constant friction. The atmosphere is dragging on the surface, or the surface is dragging on the atmosphere, depending on how you look at it. And angular momentum is being transferred between the two. When the atmospheric circulation speeds up during one weather cycle, it can steal momentum from the surface and slow the rotation down. When the circulation slows, some of that momentum flows back, and the surface speeds up slightly. And this is where it gets strange, because these atmospheric cycles on Venus might last decades. Maybe longer. We don't have enough data to know. The Magellan mission saw one snapshot. Venus Express saw another. The difference between them could be a long-term trend, or it could be one wave in an oscillation. We simply haven't been watching long enough. Now, let me tell you about the coincidence. It might be nothing, but it's the kind of nothing that keeps physicists awake at night. Every time Venus makes its closest approach to Earth, roughly every 584 days, Venus presents almost exactly the same face to us. The same hemisphere is pointed at Earth during every close encounter. 5 Venusian solar days fit almost perfectly into that 584-day interval. The number is 5.001444. That's not 5, but it's very close to 5. Is this a genuine physical resonance? Is Earth's gravity, feeble as it is at that distance, somehow tugging Venus's rotation into a precise relationship with Earth's orbit? Or is it just a numerical coincidence, the kind of accidental near match that happens all the time when you have a lot of numbers floating around? Gould and Soter, the same pair who proposed the atmospheric tide theory, had an argument for why this might be real. If the two dominant torques on Venus, the gravitational body tide and the thermal atmospheric tide, nearly cancel each other out, then the net torque on Venus is very small, and in that regime, even a tiny additional force, like the gravitational pull of Earth during close approaches, could be enough to tip the balance and lock the rotation into a resonance. It would be like two equally matched arm wrestlers, neither one budging, and then a child puts one finger on one of their hands, and that's enough to decide it. But more recent work has been skeptical. The consensus now seems to be that Earth's gravitational effect on Venus is too weak to explain the near resonance. It's probably a coincidence. Probably. But then there was this paper by Codal in 2010 that proposed something truly wild. Maybe it's not the whole planet that's in resonance with Earth. Maybe it's just the core. If Venus has a liquid outer core surrounding a solid inner core, and there's some friction at the core mantle boundary, the inner core could behave somewhat independently. The mantle rotates at its own pace, pushed and pulled by the atmosphere, but the dense iron-rich inner core, deep below the surface, responds to gravitational forces differently. It could be in a resonance with Earth's tidal pull, even while the mantle is not. The core and the mantle would be decoupled, spinning at slightly different rates, with friction at the boundary, allowing them to exchange angular momentum, but not forcing them into lockstep. I find this image extraordinary. Deep inside Venus, beneath 800 kilometers of rock and a layer of liquid iron, there might be a solid iron heart slowly, silently turning at a rate dictated by Earth's gravitational rhythm, a hidden clock, synchronized not to its own planet, but to ours. The surface is buffeted by hurricane-force winds and scorching heat. The atmosphere is a swirling cauldron of acid, and down at the center, the core quietly follows a beat we set. Is it true? We have no idea. To test it, you'd need detailed measurements of Venus's internal structure. You'd need a seismometer on the surface, or very precise gravity measurements from orbit over a long period. We don't have either. And that brings me to the warning I want to issue. In physics, and especially in planetary science, there is a constant temptation to pick the theory you like best and promote it as the answer. The giant impact is dramatic and satisfying. The atmospheric tides are elegant and self-consistent. The resonance with Earth is tantalizing and mysterious. Each one makes a good story. And human beings love good stories. We are storytelling animals. We'd rather have a neat narrative than a messy truth. But the messy truth is that we do not know what happened to Venus. All three suspects, the impact, the atmospheric tides, and the resonance, are plausible. They are internally consistent. They can be made to fit the data. But the data is sparse. We have the rotation rate. We have the fact that it's retrograde. We have one measurement of its change over 16 years. We have no moon samples, no surface chemistry, no seismic data, no long-term rotation monitoring. We are trying to solve a murder with one footprint and no witnesses. And that's not a failure. That's the current state of the investigation. Any detective who tells you they've closed the case when all they have is circumstantial evidence is either lying to you or lying to themselves. The good detective says, here's what the evidence supports, here's what it doesn't, and here's what I'd need to make an arrest. What would we need? Let me lay it out. First, we need to know what Venus looks like on the inside. On the inside, we need to know what is the core solid or liquid? Is there a solid inner core? How big is it? What's the density profile? This information would tell us about tidal dissipation and whether the resonance hypothesis has any chance. You could get some of this from very precise Doppler tracking of an orbiter, measuring tiny variations in the planet's gravity field. Better still, you'd want a seismometer on the surface, but that's brutally hard. Let me tell you about the Venera program, because it tells you something about what we're up against. The Soviet Union sent a series of probes to Venus, starting in the early 1960s. The first few were crushed by the atmosphere before they even reached the surface. The engineers hadn't expected the pressure to be that extreme. Nobody had. They redesigned the probes, made them stronger like diving bells, sealed titanium shells rated for enormous pressures. Venera 7 made it to the surface in 1970. It transmitted for 23 minutes before going silent. Venera 9 sent back the first photograph ever taken on the surface of another planet. A grainy panoramic image of flat rocks under a dim overcast sky. The light on Venus is eerie. Despite being closer to the sun, the surface is darker than you'd expect because those thick clouds block most of the sunlight. What gets through gives everything a brownish-orange cast, like being inside an oven with a dirty window. Venera 13 in 1982 lasted about 2 hours and 7 minutes. It sent back color photographs showing flat slabs of basaltic rock, some of them cracked and weathered, stretching to a hazy horizon. You can see part of the lander in the frame, the edge of the spacecraft sitting on this alien rock. And then the signal died. 2 hours. That's all we got. The heat ate the electronics. The pressure crushed the seals. Sulfuric acid corroded whatever was left. Every photograph from Venus was taken in those desperate minutes before our machines were destroyed. That's the closest we've come to touching that planet. Second, we need long-term, high-precision measurements of Venus's rotation. Not 2 snapshots 16 years apart. Decades of continuous monitoring. Is a 6.5-minute slowdown part of an oscillation that averages out over centuries? Is it a one-time trend? Is it random noise from chaotic weather? We can't tell from 2 data points. You wouldn't diagnose a patient from 2 blood pressure readings taken 16 years apart. You need a time series. That requires a dedicated orbital mission or a network of radar stations monitoring Venus over decades. Third, and most ambitiously, we need samples. Rocks from Venus's surface that we can bring back to a laboratory and analyze for isotopic signatures. If a giant impact occurred, the chemistry of the rocks might carry a record of it, the way moon rocks carry the record of Theia. If Venus once had a moon that was reabsorbed, there might be subtle isotopic anomalies in the crust. The ratio of certain elements, tungsten isotopes for instance, or siderophile elements that tend to concentrate in planetary cores, could tell us whether foreign material was mixed into Venus's mantle by a collision. But getting samples from Venus is orders of magnitude harder than getting them from Mars. The surface temperature melts tin and lead. The pressure would crush most containers like a paper cup in the deep ocean. The atmosphere corrodes metals with sulfuric acid, rain. Any sample return mission would be an engineering feat unlike anything we've attempted, requiring materials and electronics that can survive long enough to drill into rock, collect a sample, seal it, and launch it back into space through 93 atmospheres of carbon dioxide. We don't have that technology yet, but we might within a few decades. And when we do, Venus might finally give up its secret. None of these things are easy, but none of them are impossible. And that's what makes Venus's backward spin such a living, breathing mystery. It's not a dusty case from the archives. There are new models being published every few years. There are new missions being planned. The investigation is ongoing. Let me step back and tell you what this whole thing teaches us about physics itself. When I was learning about the solar system as a student, the picture they painted was orderly. Conservation laws reigning supreme, angular momentum perfectly preserved, planets formed neatly from a spinning disk, all going the same way like clockwork, and that picture is mostly right. But in physics, mostly right is a very important phrase because the gap between mostly right and completely right is where all the interesting science lives. Venus spinning backward. Uranus tilted so far on its side that it practically rolls along its orbit, its axis, nearly parallel to the plane of the solar system. Whatever hit Uranus, if something hit it, must have been enormous. And there's an interesting contrast. Uranus has moons, lots of them. And they orbit neatly in the plane of Uranus's equator, which means they orbit nearly perpendicular to the plane of the solar system. That suggests that if an impact tilted Uranus, it happened before the moons formed, or the moons formed from debris generated by the impact. Venus has no moons, no ring system, nothing orbiting it at all. Whatever happened to Venus left the planet stripped clean and alone. And then there's Neptune's largest moon, Triton, orbiting in the wrong direction, clearly a captured object that wandered too close and got trapped in Neptune's gravity. Mercury locked into a peculiar 3-to-2 resonance with the Sun instead of the 1-to-1 tidal lock you'd expect because its orbit is just eccentric enough to prevent synchronous rotation. Each of these is an exception to the simple story. And each exception is a window into something that happened, some process that disrupted the orderly expectation, some event or interaction we haven't fully accounted for. If everything in the solar system obeyed the simple story perfectly, we wouldn't learn very much from studying it. It's the deviations that teach. Every anomaly is a question the universe is asking us, and the quality of our science is measured by how honestly we engage with those questions. Are we willing to sit with uncertainty? Are we willing to say, this is interesting and I don't understand it yet? Or do we rush to an answer because the uncertainty makes us uncomfortable? I'll tell you something, the uncertainty is the best part. It means there's still something to discover. When all the questions have been answered, physics becomes accounting. As long as Venus is spinning backwards and we can't explain why, there's something profound about the formation and evolution of planets that we haven't grasped, and that should excite you, because the next piece of evidence, from a future mission, or a new model, or a lucky observation, might crack the case wide open. Venus is not misbehaving. Venus is following the laws of physics with perfect fidelity. The equations of motion are satisfied. Angular momentum is conserved across the whole system, even if not within Venus itself, because torques from the sun and from the atmosphere are acting. The planet is doing exactly what physics says it should do. The problem is entirely with us. We haven't identified all the forces, all the events, all the interactions that produce this particular outcome. And until we do, Venus's backward spin will remain one of the great open puzzles in planetary science. I want to leave you with one more thought, and this is the one I feel most strongly about. Venus is often called Earth's twin. Nearly the same size, nearly the same mass, nearly the same density, formed from the same stuff in the same region of the protoplanetary disk, at nearly the same distance from the Sun. If you knew nothing about these two planets except their basic physical properties, you'd predict they should be nearly identical worlds. And yet one has blue oceans and forests and people arguing about physics, and the other has a surface hot enough to melt lead, an atmosphere of carbon dioxide and sulfuric acid, and a backward spin that we can't explain. Somehow, in the 4.5 billion years since both planets formed, they diverged catastrophically. Earth went one way, Venus went another, and the rotation is part of that divergence. A planet's rotation affects everything. It affects the weather patterns, the magnetic field, the tidal interactions, the distribution of heat. A planet that spins slowly has different atmospheric circulation than one that spins fast. A planet that spins backward has sunrises in the west, and a Coriolis effect that works in the opposite direction from what you'd expect. The rotation of Venus isn't just a curiosity. It's a piece of the puzzle of why Venus became the hell world it is today while Earth remained habitable. Understanding the rotation might help us understand the divergence, and understanding the divergence might help us understand what makes a planet livable. That's why this question matters beyond astronomy. It matters for understanding our own planet, for understanding what could go wrong, for understanding the razor-thin margin between a world where life flourishes and a world where lead melts in the afternoon sun. There is a tendency in how science gets communicated, and I see it everywhere, to present results as more settled than they are. People want answers. They want the mystery wrapped up neatly with a bow on it. They want the detective to point at the suspect and say, he did it. And sometimes the detective can do that. Sometimes the evidence is overwhelming and the case is closed. But sometimes the evidence isn't there yet. And the honest thing to do is say so. The willingness to say, I don't know, is not a weakness. It is the foundation of honest science. The moment you start pretending you know more than you do, you stop looking. You stop questioning. You stop doing science. And I worry about that. I worry about it in physics. I worry about it in every field. Because the problems that matter most are usually the ones where the answers aren't clean. They're messy. They resist simplification. And they require patience. The patience to gather more data. The patience to test models against observations. The patience to hold 3 contradictory ideas in your head at once and not panic. Venus teaches patience. It hid its rotation for 3 centuries. It hid its surface behind clouds of sulfuric acid. It destroyed every machine we sent to its surface. And it's still changing, still evolving, still keeping secrets. That's not frustrating. That's wonderful. That's exactly what a good mystery should do. It should resist easy resolution and reward persistent inquiry. Venus is spinning backwards slowly in the wrong direction, showing the same face to us every time we pass by, its rotation still changing in ways we can barely explain, hidden beneath a poisonous atmosphere so thick it kept it secret for 300 years. Every theory we've proposed has merit. Every theory has holes. The planet is patient. It has been turning this way for billions of years. It can wait a little longer for us to figure it out. Here's what I'd ask you to think about. If you had to choose one suspect, which would it be? The catastrophic impact, the slow atmospheric reversal, the hidden resonance with Earth, or something nobody has thought of yet? Because somewhere in that question is a lesson about how the universe actually works, which is usually messier, more layered, and far more interesting than any story we try to tell about it. What do you think happened to Venus?